This video is part of a course on food physics, of which this is the application section. This one's on air drying, and this particular topic is in 5 parts, and this one is the last part of this 5-part series. The series talked about different approaches from more complex to less complex of looking at the physics of drawing. This video simply summarizes those approaches. The details are in those individual videos earlier in this series. The learning outcomes, not just for this video, but for the entire series, is here. You're welcome to pause this video and look at these. They have been described in detail in the very first video. A good framework to think of drawing of food is to think of the food as a porous medium with various phases. So for example, the solid phase, which would be like the carbohydrate, and then there is liquid water in there. There is also vapor in the gas spaces, and there is air. Okay, so in this system, there is multi-phase transport, meaning transport of water, vapor, and air by their respective mechanisms. For example, water by capillarity or vapor by molecular diffusion. There is also equilibrium between water and vapor. For all practical purposes, this equilibrium holds locally, and then there is also energy transport. So energy transport also has the various modes like conduction in the various phases, but also when the fluids flow, like the water or vapor flows, they carry energy with it. This is how we want to look at a drying process. We discussed the understanding of the physics of air drying using 3 different approaches that are progressively more mechanistic. We discussed them in individual videos, and we discussed them in reverse order. So this one is described, the most mechanistic one is described in video 2, and the lesser mechanistic is in 3, and the least mechanistic is in 4. At the most mechanistic end of the spectrum, we describe drying using multi-phase transport. So a phase of water, vapor, and air, or vapor plus air, transport with distributed evaporation. So this evaporation term is distributed throughout the food, and also deformation. So this is not everything. The deformation equation I'm not including. They also tend to be quite complex. So this is how we are trying to describe the drying process in the most comprehensive mechanistic way, and by doing that we can get a time variation, spatial variation of water vapor, temperature, and also deformation. So very comprehensive set of information. For each phase, we have a conservation equation that simply says a conservation of mass for that phase. And each conservation equation is written in terms of some fundamental physics. So for example, the water transport is written in terms of capillarity, and if evaporation, that is a negative source term, and for not so intensive drying, we are ignoring any pressure-driven flow. Likewise, for the vapor phase, we have a similar evaporation term that is not seen here, and then we have a binary diffusion, and then again we are ignoring for this less intense heating any pressure driven flow. For temperature, we describe by using the energy conservation equation that has heat conduction in all of the phases, solid and liquid and vapor and air, and the latent heat from evaporation, and when those phases are moving, they are carrying energy with them. All these physics are included in this description. Being most comprehensive, it is also the most complex. Reducing details but still staying mechanistic, we get this diffusion equation description of the drying process. It still describes moisture as a function of position and time, but it does not have the multi-phase aspects of water and vapor. It is described using a moisture diffusivity. That moisture diffusivity is a combined moisture diffusivity for water and vapor. It's an effective value that is obtained from the experiment, and sometimes it's obtained from the very same experiment that we are fitting the model, making this effective diffusivity dm somewhat of an empirical quantity. Various approaches to evaporation is used. Often evaporation is considered at the boundary. Now, this is a considerably simpler description of the physics that can be solved easily, understood using even analytical solutions, but it is at the cost of losing all these detailed information for different phases like water, vapor, and also obviously it does not have the deformation aspect. Reducing the details even more, we get to this lumped parameter description of the physics of drying. So here spatial variations are ignored. It is only a function of time, meaning it is written in terms of the average moisture of the solid. It is pretty much the simplest description, and its applicability is the most restricted. It often is an empirical description. So as we go from least to most mechanistic, we get increasing amount of detailed understanding, but at the cost of more computation and more data that is needed, it takes more time and so on. Many of these less mechanistic models go by names. For example, a version of this equation is called the Lewis model, and then this one is sometimes called the Fick's second law approach to studying drying. Let's go a little more into what is ignored in the respective models and their implications. So in the most comprehensive model, although pressure driven flow can be included in the series of videos that we prepared, this is for less intensive heating, so we have ignored pressure driven flow, which means we have dropped these terms and this equation, and so this is the only thing that we ignored. Pretty much all other physics were included. The next lower mechanistic class of models, that's the diffusion equation and its application, it is actually quite a bit simpler. It's a precipitous drop from all the physics that we just discussed, making it at times almost a semi-empirical approach to understanding drawing. It only assumes diffusional transport, which means pressure driven flow, for example, is definitely ignored here. This is ignored, and then um, what that means is if we have more intensive heating or any kind of volumetric heating like radio frequency or microwave, this is not going to work at all because that physics itself is missing. Then temperature changes are often ignored because drying is often limited by mass transfer. So at least written in this format, it's ignoring the temperature changes. And then if we get into the constant diffusivity and analytical solution to this equation, that brings us a long list of limitations. So for example, we are ignoring shrinkage, then we have to do regular shapes for analytical solution, and it has to be for constant diffusivity, and so boundary conditions has to stay constant, it cannot change with time, and then evaporation can be handled at surface only. Those are quite a few limitations that we have to keep in mind when we use this equation and its analytical solutions that are very, very widely used. If we use numerical solution and then we can allow, for example, the diffusivity to vary with moisture content, or boundary conditions can change with time. That will improve some, but we have to remember that it does not even have physics like pressure driven flow. Reducing the details even further, we get into the lumped parameter model, and the lumped parameter model, it really does not have the detailed mechanisms at all, and of course it ignores all of the other things that we have talked about, and so this often ends up being almost like an empirical model. So it ignores, for example, all of these, and so in general it is not a very recommended way to look at the physics because it doesn't tell us much about the physics. It may be quick for some applications to get a quick answer, but it's not really giving us the physics, the understanding of the physics or the mechanistic understanding. So of these three approaches to understanding a drying process, mechanistic understanding, which one do I choose? Well, that depends on the end goal. The simpler models of the first two of the three that we discussed, the lumped parameter model and the diffusion model with constant parameters and so on, are okay when there is no need for mechanistic understanding, when the model is going to be used for just process control purpose. and sometimes even trial and error is sufficient for optimization. So we don't need to understand all of the physics for the optimization. And in research, when some other physics is the focus. So for example, this could be combined with mechanics. This could be combined with high pressure or such processes that have their own physics. Then it may be useful to keep the drying physics simpler. Whereas the complete multi-phase model would be the right one when there is need for mechanistic understanding and in complex drying situations, like for example in a combined drying like microwave drying, or let's say sequential drying. You're doing 2-3 different drying process at the same time. Also where optimization of the drying process makes a huge difference, not a small difference, but it will mean a big time in terms of scale up, for example, of a process. Then it is worth going for the complete or the most complex version of the physics, and that will give us the most comprehensive understanding of the process. Now, the temperature, moisture, and other such primary variables coming out of the physical descriptions that we discussed is great, but that may not be enough in a food drying process where we are really ultimately interested in the quality and safety of the dried products. So how do we understand quality mechanistically? Now, suppose our quality really is involved, has to do with how porous the food is, or how much case hardening is forming in the food. If this is all we need in terms of quality, from the more mechanistic description of the food process that we discussed, the food drying process that we discussed, that will give us the porosity. We don't need to measure and supply. That will actually predict the porosity for us or predict the case hardening. Now, the other kind of quality, let's say how much is the nutrient destruction, or how much is the color degradation or some color formation, or how much flavor components are generated. To obtain these, we note that the the descriptions that we had, they give temperature and moisture, for example, at any location and at any time. So now we combine that temperature location of in the food over time, or the moisture in the food over time, with the kinetics of, let's say, nutrient degradation, which could be a first order kinetics, or which kinetics of color, which can be a Maillard reaction that we know, and likewise for flavor. So by combining the temperature at a location with the kinetics, which has to come separately from other measurements, by combining the kinetics and the temperature and sometimes the moisture level, I get the quality at any location. And then we can average this over the entire food. We can average this over the entire food to get its quality. In fact, this also can be done for texture, where we can relate, let's say, the moisture level of the food with a modulus of the food, the Young's modulus, for example. And this can vary over the entire food material, and so we can get a modulus that varies with position and time, and from modulus at different positions at any given time, we can average out and get an overall modulus, which would be a measure of texture. Those are just examples of how we can get other quality parameters. Microbial or carcinogen safety can also be understood the same way. The microbial kinetics at any location can be combined. Let's see, at any location can be combined with temperature history or moisture history to get either the microbial destruction or microbial growth at that point, and therefore we know throughout the food what the situation is with the microbial load, and from that either we find where we have the maximum growth or where we have the minimum destruction, as the case may be. Likewise, for, let's say, acrylamide, we can combine the temperature history at any location with the kinetics of acrylamide formation, and thereby get acrylamide formation throughout the food, and then we can get an average formation. So what we are doing is, by combining the mechanistic understanding of the temperature and moisture physics with these quality and safety kinetics, we are getting a much more comprehensive understanding of quality and safety of the food. I know the quality and safety I described very quickly. That's because there are detailed modules on each one, quality and safety, available as part of this set of videos for the food physics course. So the reader or the person listening is referred to those videos for quality and safety. So this concludes the 5-part series on the physics of air drying. Hopefully, this would give us an improved physical understanding of the drying process. And when we use one set of physical description or a model to describe drying, what we have done should help to know what is ignored in that description, what parameters have not been considered, and so on. So we are more aware of the limitations of the description that we are using. Now, this description or the set of descriptions are not limited to just air drying. It can be other types of drying with some changes in the description. It is also extendable, much of it is extendable to processes that we normally don't think of as drying, like baking and frying. What's next? The most relatable set of videos to this one in our applications series would be on microwave drying. So if the reader has interest there, I would refer to that one. The other possibility is going back to the fundamentals. If we have to brush up fundamentals, or if we are wondering about some of the details, Then if we go to the theory series, there is a module on lump parameter, one on single phase heat and mass, and one on porous media that really develops these equations from scratch. So everything is included there, and the reader is referred to those sections for the complete details. Otherwise, this completes the section on, or the series on air drying. Thank you.